Alright, in this video we're going to talk about the inverse cosine function. Now, if you haven't watched the video that I did about the inverse sine function, I would advise you to watch that one before you watch this one about inverse cosine, because there I explain in more detail than what I'm going to do here, why we have to do certain things that we're going to do here. I'll mention those things here, but not explain them as much as I did in that first video that I did about the inverse sine function. Alright, but we want to find the inverse cosine function. So we have up here the graph of the function y equals cosine of x. Right now, if you recall things that we talked about for inverse functions, in another video that I did just about inverse functions in general, in order for a function to have an inverse, it has to be 1-to-1. Right? And for a function to be 1-to-1, that means for each y value, there's only one x value, which means the graph has to pass what we call the horizontal line test, right? Meaning a horizontal line, if I draw it through the graph, it can only touch that graph one single time. That makes the function 1-to-1. Now, the graph of the cosine function is pretty obviously not 1-to-1, right? If I draw a horizontal line anywhere in the range of the cosine function, which is between -1 and +1, a horizontal line anywhere in there is going to intersect that graph an infinite number of times. Right? Remember, this is not the entire graph of cosine. That wave goes in both directions forever. Right? So if I draw a horizontal line there, it's hitting that graph an infinite number of times. All right? So the graph of y equals cosine x, or cosine x, is not a 1-to-1 function. Right? It's not. So you would think, well, if it's not a 1-to-1 function, we can't have an inverse. But we need to have an inverse, right? Because there's a lot of different types of problems that we'll see, that we'll get to in other videos that I'll be doing in the future, where I know the y here, and I want to figure out what the x is. I know the output of the cosine function. I need to solve for the input. Well, I can only do that if I can take the inverse of the cosine function. Just like if I had the function, x plus 3 equals whatever. Well, the inverse of plus 3 is minus 3. So in order to solve for x, I have to do the inverse of plus 3, and I subtract 3 from both sides. Well, if I have a number equals cosine of x, in order to solve for x, I need to do the inverse of the cosine function. So I need to have an inverse cosine function in order to be able to solve a lot of different types of problems. All right, so what we do, and just like similar to what we did for the inverse sine function in that other video that I was talking about before, we need to limit the domain of the cosine function in order to make it 1-to-1. Right, so what I want to do here is I'm going to erase parts of the graph of the cosine function to make it 1-to-1. Right, so I want the entire range of cosine to be covered, so I still want all my values to go between -1 and +1, but I only wanted to hit each one of those y values one single time. So what I'm going to do is start at 0, right, erase everything to the left of 0, right, that's where I have a y value of +1, and then it goes down to a y value of -1 at the x value of pi, so everything to the right of that I'm also going to erase, and what I get here between 0 and pi, between x equals 0 and x equals pi, I get every y value from +1 down to -1, and I only hit each y value one single time. This function now is 1-to-1. Right? So if I limit the graph of the cosine function where x is in between 0 and pi, I get a 1-to-1 function. Right? This graph here passes the horizontal line test. Right? No matter where I draw a horizontal line, it's only going to hit that graph one single time. Therefore, it's 1-to-1. Therefore, this function here is going to have an inverse. Right? So again, if you watch the video that I did on the inverse sine function, we did something very similar there, but for the inverse sine function, we had a different domain, right? When we restricted it, it was a little bit different, right? And that's the key difference between the inverse sine and the inverse cosine functions, are how we have to restrict the domain in order to make our graph 1-to-1 and in order to have an inverse. All right, so as we go through the rest of this and doing examples, you'll see that that's the difference between inverse sine and inverse cosine. All right, so this is my restricted graph of the cosine function, x just between 0 and pi. That gives me all the y values between -1 and +1, and it gives me each y value only one single time. That one got partially erased up there. All right, so from this function here, I can create the inverse cosine function. Right? Remember that -1 exponent, that's the notation for the inverse function. It doesn't mean cosine to the -1 power. That's the cosine inverse. Right, the inverse function notation. Right, so the graph of y equals cosine inverse of x looks like this. Remember, inverse functions switch the inputs and outputs. Right, so for our restricted domain here, the x values were from 0 to pi. Well, for the inverse function, our y values go from 0 up to pi. Right, let me put the 0 in here. Right, so from 0 up to pi, and then for the cosine function, our y values were from -1 to 1. For the inverse cosine function, our x values are from -1 to 1. Right? And notice that this graph here does have these filled in circles at the end, that means that the graph stops right there. Right? That's the entire graph of the cosine inverse function. It does not continue and keep doing waves beyond this on either side. If it did that, if this cosine thing kept going up like this, it would not be a function because it would fail the vertical line test. All right, that's why we have to restrict the domain here, why we have to make that function one-to-one, so that when we flip everything over and switch all the x's and y's, what I have is still a function. Right? The inverse function has to still be a function, which means that original one has to be one-to-one. Right? If this had more of the graph here, it would not be a function because it would fail that vertical line test. All right, so that's the entire graph of the cosine inverse function. It's the whole thing. It does not continue beyond there. That's it. Right? It's a very narrowly defined function. It's only defined for a small number of y values and a small number of x values. I did those backwards. This is the x and this is the y, but you get the idea. All right, so that's the entire inverse cosine function. So the definition of inverse cosine, the inverse cosine function, again, cosine with that -1 exponent, that's our notation for the inverse function, has domain from -1 to +1, as we see here, right? The x is stretched between -1 and +1, which, over here the y's were between -1 and +1. Again, inverses switch x and y. And the range is from 0 to pi, right? So the y values go from y equals 0 up to y equals pi, right? So cosine inverse of x equals y is the same thing as saying cosine of y equals x. Right? So when we are evaluating the cosine inverse function, basically we're going to be given the output for the cosine function and we have to find the input value. Right? Again, inverse functions switch inputs and outputs. Right? So I'm doing an inverse cosine function. They're giving me the x here. That x is the output for my cosine function, and I have to figure out what the input of cosine would be to give me that x, that output. That's my output for the cosine inverse function. I hope that made sense. It sounded confusing as I was saying it. I mean, it made sense to me, but I know this stuff very well. Right? So inverse functions switch inputs and outputs. Now, if you watch the videos that I did on the sine inverse and all the examples that I did on the inverse sine function, then you kind of know what I'm talking about as far as switching the inputs and outputs. And when we do some examples for cosine inverse, it'll be a little more clear what I'm talking about there. Right? One other thing up here before we do an example or two, this is also called the arccos function. Right, so there's two different notations for the inverse cosine. There's that cosine with that -1 exponent, right? That's the cosine inverse, and also arc cosine, ARC, and then cosine, right? Arc cosine refers to the arc of a circle and trying to measure the length of an arc. And you use this inverse cosine function in order to measure the arc of a circle. That's a problem that we're not quite ready to do yet based on what I've done in these videos so far. But eventually I'll get to a point making these videos where we do a problem like that. And when we do, I'll try my best to remember to point out, this is why we call it arc cosine instead of just cosine -1, because it helps us measure the length of the arc of a circle. All right, but we'll get to that at some future time. All right, so that's the inverse cosine function. That's all the information that you should know about it. Again, if you saw the stuff I did on inverse sine, it's very similar, but it's different, right? Because for the inverse sine, we limited the domain a different way, and we were using different values here. And so when we evaluate the inverse cosine functions, we're going to be using different part of the unit circle than what we did for inverse sine, right? So that's really the key difference between those two. Otherwise, it's pretty similar, right? So I'm going to pause the recording here and maybe erase this up here and put up an example or two where we can evaluate the inverse cosine function just so you get an idea of what it's like to do that. Alright, so I put up here an example. We're going to evaluate cosine inverse of 1/2. Right? And I put up here the unit circle. Now notice I only labeled part of the unit circle. When we're evaluating the inverse cosine function, we're only using the top half of the unit circle. And the reason for that is because the definition of the inverse cosine function, the range is between 0 and pi, right? So when I'm going to my unit circle, I'm only looking at the part of the unit circle that goes between 0 and pi, 0 being on the positive x-axis, and then going around the top half of the circle where pi is over at the negative x-axis. So my values for cosine inverse have to come from that top half of the circle, in between 0 and pi, because of the way that we had to, if you remember the graph that was up here before, we had to limit the domain to just be between 0 and pi, right? So when we use the unit circle, we just go between 0 and pi. We only use that top half of the unit circle. And if you watch the video that I did on the inverse sine function, remember the inverse sine function was only the right half of the unit circle. That was between negative pi over 2 and positive pi over 2. The inverse cosine function is different because we had to, chop off parts of that graph differently for sine and cosine graphs in order to make the graph one-to-one, right? So that's the key thing to remember. The key difference between inverse sine and inverse cosine is which part of the unit circle you have to look at in order to evaluate it, right? So for inverse cosine, we're just looking at the top half, just between 0 and pi. And if you understand where that came from, that's why I showed you the graph before and erased part of it. If you understand that that's where it came from, it makes it easier to remember which part of the circle you're looking at. Just kind of picture the graph of cosine. I have to take between 0 and pi to get that part of the graph. Okay, so I have to go to my unit circle between 0 and pi. Right? It all fits together. I try to show you as many different aspects of these things as possible so that you can make those connections and really understand what's going on. All right, let's get to actually evaluating this now. Cosine inverse of 1/2. All right, so what this is asking me, right? Remember, cosine inverse is the inverse of the cosine function, and it switches the inputs and outputs. So really what this is asking is, I have the cosine of something is going to give me the output of 1/2. Right, so cosine of some number is going to equal 1/2. Whatever that number is, that's what cosine inverse of 1/2 is equal to. Right, so when I'm evaluating the cosine inverse function, I'm looking for this output value, right, 1/2. Right, remember, the cosine function, when I do the cosine of some number, and I'm looking at the unit circle, the definition of the cosine function is the x-coordinate of your terminal point. Right, so for cosine inverse, I'm looking at the top half of the unit circle, and I'm looking for an x-coordinate equal to 1/2. All right, so top half of the unit circle, I'm looking at x coordinates, and realize this, when I'm looking at the top half of the unit circle, my x values go from 1 and then down to 0, and then negative x values over there in the second quadrant to -1. So that top half of the unit circle gives me all the x coordinates from +1 to -1, right? Which is why I'm using that top half of the circle. All right, and it gives me all those x coordinates only one single time. All right, so where is x equal to 1/2? Well, that's up here, right? That point up there, and if you recall from your trig end, if you haven't seen the videos I did on trig end, you should check those out. That's this finger here, gives you 1/2 root 3 over 2, and that finger represents pi over 3. Right, so cosine inverse of 1/2 equals pi over 3, right? Because cosine of pi over 3 equals 1/2. All right, so that's the relationship between the cosine and the inverse cosine functions. All right, so when we're trying to evaluate inverse cosines, the two key things we need to realize. First, cosine inverse tells me top half of the unit circle, my answer has to be a number between 0 and pi, right? 0 on this side to pi on that side, right? And then for cosine inverse, I'm looking for the x-coordinate of whatever that number is that's in the parentheses, right? So I want to find an x-coordinate of 1/2, and then whatever the pi number is that gives me that x-coordinate of 1/2, that's my result, right? Because if I do cosine of pi over 3, I go to my unit circle to pi over 3, the x-coordinate of that point is 1/2. All right, so that's evaluating the inverse cosine function, the definition of the inverse cosine. All right, so I'm going to stop this video here, but I'm going to make another one where I just do more examples like this, where I just evaluate some more inverse cosine functions for different numbers. So check out that video so that you're aware how to do it. And the more of it you see, the easier it becomes. Like I said, there's just a couple things. You have to know cosine inverse is the top half, and then when it's cosine, I'm looking for the x-coordinate. If you understand that part, the rest of it is just knowing the unit circle and being able to locate the numbers that you're looking for. All right, so make sure you check out that other video that I'm going to do with more of these examples.